Hi kids, video 17 is on the force energy theorem, which is essentially the question, how is energy transferred or transformed? This question is a really big deal in the real world because it helps us solve problems from all different branches of physics. So this is really a concept that is worth thinking quite a bit about and learning thoroughly. Okay, so the force energy theorem basically describes what happens in an open system for energy. So if we start off with an object of interest, for example this stroller, the stroller has primarily kinetic motion energy as it's moving, but that energy comes from a place outside of the system. Specifically, the energy comes from kinetic energy from Dad. So that would be a positive delta energy, positive change in energy as the Dad is pushing the stroller as it moves. That stroller also will be losing some energy as it moves. We have a negative delta ET, which is energy loss from the friction of the wheels in that stroller as they're rubbing against the ground. So the overall delta energy for this stroller system might be positive, it might be negative, it might be zero, depending on how those energy inputs and outputs balance. You could write in a little equation to describe this, right? The change in motion energy of the stroller is going to be equal to the input energies, delta EC from the Dad, minus all of the output energies, delta ET from the ground. This is not like a big master equation that you'll use again ever. It's specific to this system, but it basically describes conservation of energy in an open system where it is moving in and out. So it turns out that the way that energy moves in and out of open systems is through a force. You probably have a working definition about what force means, but in terms of physics, it's any push or pull or contact between two objects. Force will be a new variable for us. The symbol that we're going to use to represent force is capital F, and the units for force are the Newton, or capital N. Before we start talking about how forces can cause that change in energy, I want you to have a sense of how large and small the values of forces can be. A little beetle pushing a dung ball there, that's going to be less than 1 Newton. So some sort of fraction of a Newton, that's going to be a very tiny amount of force. Our classic pineapple that we talked about a lot from the last unit has a gravitational force or a weight of about 10 newtons. So if you're holding a pineapple, the amount of force you feel is 10 newtons. Something like a race car parachute, to slow it down there, is going to be exerting thousands of newtons of force on the race car. And of course, a space shuttle would be on the order of millions of newtons as it's launching. So there are two relationships that describe the overall delta E, or the delta E in any part of an open system. And the first relationship has to do with forces. So if you just imagine which of these two horses is going to change the energy of a cart more. We've got a mini horse and a big horse. Of course, the mini horse is able to pull on the cart with a small force, and you'll probably predict that that results in a small change in energy for the cart. If you are a big horse and you can pull with a large force, that's going to cause a larger change in energy for the cart. So small force, small delta E, large force, large delta E. Hopefully that all screams linear relationship to you, and you would say that there is a linear relationship between the amount of force and the amount of change in the energy of a system. The second relationship is a little bit trickier to kind of visualize, but the big idea is that in order for a force to actually work, in order for the force to actually change the energy of an object, it has to act as it pushes or pulls the object through some kind of distance. So I've got 3 skateboarders here, right? I've got this person standing on the skateboard flat, and I've got this person riding a short ramp, and then I've got this crazy person that's going down a massive skateboarding ramp. In all cases, the force is about the same. It's the force of gravity that is acting between the person and the skateboard, right? The earth is pulling down on that skateboard about the same on all three of those people. But we have a really different impact on the change in energy of those systems based on the amount of distance that gravity is allowed to pull. For that first girl, right, gravity doesn't actually get to pull it down because it's already on the ground. So the distance the skateboard moves is 0. And consequently, the energy of that skateboard isn't changing either. That first guy in the ramp allows gravity to pull it down, right, probably about a meter as he gets pulled down that first piece of the ramp. That's a small delta D, and it causes a relatively small change in energy on the skateboard. It gains some energy, but not that much. This third example, of course, has a much, much larger change in distance as that gravity pulls it down that huge ramp, and that's going to cause a much larger change in energy. So again, you'll see a scenario where the smaller the distance, the smaller the change in energy, and the larger the distance, the larger the change in energy, making an overall linear relationship, again, between distance and delta E. So the new equation for this unit, which is known as the force-energy theorem, comes from those two relationships. Delta E has a linear relationship with force, and delta E also has a linear relationship with delta D. So please take a second and write down what you think the ultimate equation for delta E is before you move on in the video. Hopefully you came up with this guy right here. Delta E is equal to force times delta D. So if we now take a minute to go back to that stroller system from the beginning of the video, we can actually do a much more thorough analysis now of exactly how much the energy of that stroller is changing as it gets pushed. Because we can calculate the amount of chemical energy that Dad is losing. The amount of chemical energy Dad is losing is going to be equal to the amount of force Dad is pushing on the stroller times the distance that the stroller is being pushed. So the more force Dad pushes on the stroller, the more energy it's going to take. And the farther Dad pushes the stroller, the more energy it's going to take, which should all make sense. There's going to be that negative delta energy as well. The higher the force of friction between the stroller and the road, the more energy it's going to lose, and the more distance that the stroller rolls on the road, the more force it's going to, or the more energy it's going to lose as well. So all of these values now are things we can estimate. While it would be hard to just from, the very beginning estimate how much energy Dad was losing and how much energy Dad was providing and how much energy the stroller was losing due to friction, all of these things, the forces and the distances, are things that you can either measure or estimate much more accurately. So you actually can figure out how much the energy of your open system is changing over time, which is a really powerful thing to be able to do. So please take a minute and summarize, revisit that essential question, which is how is energy transferred and transformed in an open system? Thanks for watching.